Good day, and you are all welcome to Algebra Academy YouTube channel. In our last video, we explained the concept of hybridization in organic compounds, and we explained the hybridization of carbon atoms. We also explained the hybridization of hydrogen. And if you remember very well, we mentioned that organic compound contains carbon atom, hydrogen atom, and other atoms like phosphorus, oxygen, nitrogen, sulfur, and so on and so forth. And carbon being the backbone of organic compounds, the hybridization needs to be well explained, and that was what we did in the last video. And there, you remember vividly, we said hybridization, it involves the mixing or blending of orbitals of the same principal quantum number to form hybrid orbitals, and that's just hybridization. And we're able to hybridize or check the hybridization of carbon and how hybridization is actually formed. We have something like this. We have something like this in the last video, because carbon is 1s2, 2s2, and 2p2. That is the ground state of carbon, the configuration of the ground state of carbon. But when it gets to the excited state, we'll have 1s2. That means 2s2 and 2p2 will have been hybridized because they are both having the same principal quantum number. So when they hybridize, you now have 1s2, 2s1, and 2p3. You can check details of the last video to understand this better. So if we distribute them in their individual orbital, we have this for 1s2, which we said is not participating in the hybridization because it is in a lower energy level. That is, it does not have the same principal quantum number. You can see 2s2, 2p2, the same principal quantum number, but one is different, it's in a lower energy level. So for the 2s2, 2s1, and 2p3, when they get hybridized, we have something like this. Is 2s1, and the p3, it has 3 suborbitals, so we should name them x, y, z. So we'll be able to identify which of the p's we are talking about as we proceed. So we have one electron in each, so this is 2p3, and this is what we used to explain sp3 in the last video, that for sp3 it is 1s plus 3p, that is p plus another p. This is the p3, this is the s, that makes it sp3. That was what we did in the last video. And as a matter of fact, this configuration is what we call the excited state of carbon. So right now I want to check for sp2 and sp. So starting for sp2, the same way we did for sp3 in the last class, we said for sp2, it means 1 electron of 2s plus 2 electrons of 2p to form 3 hybrid orbitals. Don't forget, in the last video I told you that orbitals that participate in hybridization, they form sigma bonds. But orbitals that do not participate in hybridization, in other words, we can call them unhybridized orbitals, they form pi bonds. So it means we are forming 3 sigma bonds, that is 3 sigma bonds. Now, if we need 1 electron from 2s and 2 electrons from 2p, that means one of the p's will not be participating in the bonding. It means we are going to remove 1 p. Conventionally, we are removing z, so that we have x and y with 1 electron from 2s. It means for sp2 hybridization, 2pz particularly is unhybridized orbital. Unhybridized orbital. I mean, it is not participating in the bonding at all because we only need 2 of the p's, not the 3. So we're going to remove one. That one is unhybridized because it is not participating in the hybridization. Why the first 2 and 1s are being hybridized together. That means, like I said earlier, that orbitals that participate in hybridization, it means 1, 2, and 3 that are participating, that are being hybridized, they will all form sigma bond. It means we have one sigma here, but this time around it is now sp2 sigma. We have another sigma. We have another sigma here. Why the unhybridized we form pi? That means for sp2 hybridization, we're going to have 3 sigma bonds. 3 sigma bonds and 1 pi bond. Don't forget, the pi bond is formed as a result of the overlapping of the unhybridized 2pz, particularly for sp2. 2pz unhybridized orbital is what forms the pi bond. Unlike your sp3, in your sp3, which is the last lecture, we have 4 sigma bonds, 4 sigma bonds and no pi bond. And the reason is that for sp3, all the p's are participating, likewise the s. So there is no orbital that is not participating in the hybridization. There is no pi bond for sp3. So this is how sp2 is being hybridized. And one more thing is that pi bonds, when they are being orientated around carbon atom, pi bonds, they will not stand separate. They will have to stand with an existing sigma bond. This is what I'm trying to say. If this is your carbon, you have one sigma bond, you have another sigma bond, you have another sigma bond. Since this carbon is sp2 hybridized, you have how many sigma bond? 3, which is 1, 2, 3. Now the pi, because carbon is tetravalent, 4 bonds must surround it. Now where are we going to put the pi? We cannot put it here because it can't stand alone. It has to stand with an existing sigma. It is either it stands here, or you put it here, or you put it at the back in any of the existing sigma bonds. But let's just put it at the front here for better understanding. So when you see a carbon atom like this, and you see 2 bonds together, it means one of the bond is pi, while one is what? Sigma. So around this carbon now, we have one from here, sigma, another sigma, another sigma. Then the last one is pi. This is what I'm trying to say. One of these 2 will be sigma. You can just pick the one above. You can pick any one actually. This is sigma. This is another sigma. This is another sigma. And the other one is what? Is pi. So around this carbon now, we have 3 sigma bond and 1 pi bond. And that is what characterize sp2 hybridized carbon. Now that is for sp2. That is for sp2. Now for sp. For sp, that means we'll have, this is for one s1, and this is the 2s1 and the 2p3, x, y, z. 2p3, like we have it before. Now this time around, for sp, it means you need one molecule of 2s electron and one molecule of 2p. Just one. It means we need just 2 from these hybridized orbitals. One from here, one from here. That means these 2 will be left out as unhybridized orbital. We can just remove the 2 like this. These are unhybridized orbital, this and this. That means 2py and 2pz this time around. They are both unhybridized orbital. That means here now we have just one of the two S and one of the P, which is particularly X, that are being hybridized together. So to form two hybrid orbitals. Two hybrid orbitals. And don't forget, like I said, these two that are being hybridized, they form sigma, but this time around sp sigma. Sigma, sigma. Why these two will form pi, pi, 2 pi, as a matter of fact. One from Y and one from Z. That means if you have your carbon atom, or let me just say before I draw that, that's for sp, we'll have 2 sigma rather, 2 sigma bond, 2 pi bonds. So if you have your carbon like this, the first sigma, the second sigma. Don't forget, it is only sigma that can pick sides on their own. Pi, we have to stay with sigma. So you now have it this way, 1, 2. That means in every triple bond, you have 2 pi and 1 sigma. In every triple bond, you have 1 sigma and 2 pi. In every double bond, you have 1 sigma and 1 pi. Or you can have it this way, carbon atom, the 2 sigma bonds, 1 pi, another pi. So if you count around now, for this triple bond, I said 1 will be sigma, and the 2 other bonds will be what? Pi bonds, 2 pi. Don't forget that this one is also what? Sigma. So in totality now, we have 2 sigma, 2 pi, which is a characteristic of sp. If you come to this particular carbon as well, for every double bond, 1 is sigma, 1 is pi. It means we have sigma, we have another sigma, we have pi, we have another pi. 2 sigma, 2 pi. So both carbon here, they are both sp hybridized. This is as against what people say that any compound that has double bond is sp2. No, it is not every carbon that is double bonded, or every carbon that carries double bond that is sp2. Look at this carbon now carries double bond, but it is still sp, depending on the number of double bond you have in that carbon. So I will just advise that the best way to identify if a carbon is sp or sp2 or sp3 is to know the number of sigma and pi bond around it. And relatively, we have for sp 2 sigma, 2 pi. For sp2, 3 sigma, 1 pi. And for sp3, 4 sigma, and no pi. So if you use this method, you'll be able to identify the hybridization of carbon correctly, regardless of it is double bond or triple bond or all single bonds. Now we have some characteristics of this bond, of these three types of hybridization: the sp, the sp2, and the sp3. We have something we call bond length. For bond length, let's take it one after the other. For bond length, which of the three hybridization, or which of the three hybridization has the highest bond length, and which of has the shortest bond length? Now you can know the bond length of each of them by their percentage S character. What do you mean by percentage S character? Now for sp, we only have 2 participating in hybridization, which is S, 1 S and 1 P. That means on a scale of 100%, if you are to share 100% between S and P, S will take 50%, while P also takes 50%. That means unhybridized orbital, they don't take out of the 100%. They are left out because they are not participating in hybridization. So we only have 1 S and 1 P for sp. For sp2, it means we have 1 S and 2 P. We have S, we have P, we have another P. So it means this will be 33.3% or so. The same thing for this, 33.3%, and the same thing for this, 33.3%. If you go for sp3, that means we have s plus p plus p plus another p. Each will be 25% because the total percentage must be 100. 25%, 25%, and for the last p, 25%. That is just the percentage character of each of those hybridization according to the number of hybridized orbital they have. Now, coming back to bond length. For bond length, you can explain bond length with only percentage S character of each of the hybridization. Just the percentage S character. Now, the percentage S character for SP is 50%. The percentage S character for SP2 is 33.3%, while the percentage S character for SP3 is 25%. Now, the higher the percentage S character, the closer the electron cloud to the nucleus. That means when the electron cloud is very close to the nucleus, the bonds between that particular electron cloud and the nucleus will be very short because it is close. The bond will be very short. What connects the electron cloud and the nucleus will be very short. If the percentage S character is high, the electron cloud will be very close to the nucleus. That means this one will be the closest to the nucleus. This will be the closest to the nucleus because it has a very high percentage S character. Followed by this, let's say this is number 1, this will be number 2, this will be number 3. Since this is the closest, the bond that connects this particular S to the nucleus will be very short. While this one will be longer and this will be the longest. So, relatively now, sp3 is greater than sp2 and than asp. This is increasing bond length. Increasing bond length. No, let's say decreasing rather. Decreasing bond length. Decreasing bond length. I mean, as we move from sp3 to sp, the bond length decreases. As we move from sp3 to sp, the bond length decreases. It means sp we have the shortest bond length, while sp3 we have the longest bond length. That is for bond length. Now, for bond energy now. For bond energy. For bond energy, that's number 2. Bond energy. For you to know which of the 3 hybridization has the highest bond energy, it depends on the number of pi bond present. It depends on the number of pi bond present. For sp2, for sp rather, we have 2 pi bonds. For sp2, we have 1 pi bond, and for sp3, no pi bond at all. So it means if you are to check and use the number of pi bond as a k as what you use to determine the bond energy, that means our sp will be the strongest because it has 2 pi bond, followed by sp2 that has 1, and sp3 has none. So sp is greater than sp2 than sp3. This is decrease in bond energy. Decrease in bond energy. So we are using the number of pi bond to determine the one that has the highest bond energy. That is for bond energy. The last one now that we're looking at is reactivity. The reactivity, number 3. Reactivity. Now, if you check very well, your sp3 is only the characteristic of saturated hydrocarbon because there is no pi bond, they are all saturated. While sp2 and asp, they are unsaturated. But if you look at the level of unsaturation, sp and sp2 relatively, the level of unsaturation, this is more saturated than this. sp2 is more saturated than sp. Because if you look at sp rather, sp has 2 pi bond, 2 sigma bond. While for sp2, it has 1 sigma bond, 1 pi bond rather, 3 sigma bond. So if you have to count the number of bonds you want to break here now. You are breaking two bonds. Two bonds for sp, because this is sp hybridized carbon, to reach saturation. While for this, you are only breaking one bond to reach saturation. So it means this is more saturated than this. sp2 is more saturated than sp. Right now, since this one is saturated already, it will not be reactive. It will not be reactive compared to others because it is already saturated. So between these two now, we are picking the one that is more saturated. It is your sp. sp is more saturated. Sorry, sp is more reactive than sp2. sp is more reactive than sp2. So on the level of reactivity now, relatively, sp is greater than sp2 and greater than sp3. Can really learn and say reactivity decreases. Reactivity decreases. So those are the three important parts of characteristics of sp, sp2, and sp3 that we're looking at relatively. Now we need to talk about their bond angle and their shape. The bond angle of sp3 is 109.5 degree and the shape is tetrahedral. For sp2, the bond angle is 120 degree and the shape is trigonal planar. For sp, the bond angle is 180 degree and the shape is linear. So those are the shapes and angles of sp3, sp2, and sp relatively. Now we have come to the end of hybridization of carbon atoms, sp3, sp2, and sp. This is the concluding video of which I promised to do on both sp2 and sp3. Please keep watching Algebra Academy YouTube channel, and don't forget to subscribe, like, and your comment is very important. In case you have any question or you have any recommendation on any topic you want us to take, you can simply put it in the comment section. Thank you for always watching Algebra Academy.